In this video, we will learn about Deutsch-Jozsa algorithm, which is a generalization of Deutsch algorithm presented in the previous video. Let's start with the problem definition. The key difference from Deutsch algorithm is that now our function, say f, takes n bits as inputs instead of 1 bit and produces a single bit output. Our aim is to determine whether the function f is constant or balanced. A function is considered constant if all of its outputs are the same, whereas a function is called balanced if half of its outputs are ones and the other half are zeros. To understand it, let's consider the case where n is equals to 2. When f is constant, it will either produce all zeros or all ones as output. In contrast, when the function is balanced, half of its input will produce ones, for example, input 0, 0 and 1, 1, while the remaining two input 0, 1 and 1, 0 will produce zeros as output. It is important to note that any two inputs can produce zeros or ones as long as they represent half of the total inputs. Thus, when half of the inputs are the same, the function is balanced, whereas for a function to be considered constant, all input must produce the same output. How can we solve this stated problem using classical computers? Well, on a classical computer, we must examine one more than half of the total inputs. Thus, the total number of inputs we must examine are 2 raised to power n minus 1 plus 1 additional input. This implies a time complexity of big O of 2 raised to power n, which is exponential. If all of our inputs produce the same result, then the function must be considered constant, otherwise it is balanced. In contrast, on a quantum computer, we call the oracle only once. This is due to the magic of superposition. Thus, on a quantum computer, we are able to solve the same problem in big O of 1 time complexity. This represents an exponential speedup compared to the classical approach. The quantum circuit of Deutsch-Jozsa algorithm starts with two registers. The first n-qubit register is initialized with ket zeros, and the second single qubit register is initialized with ket 1. Then Hadamard gates are applied to both registers, creating equal superpositions. The superposition of all the inputs and ket minus is then passed to the UF gate. Recall, if the input to the UF gate is ket x and ket y, its output will be ket x and ket f of x XORed with y. Finally, the first register is subject to Hadamard gate once again and measured. If our measurement results in ket 0, then the function f is constant. Otherwise, it is balanced. To understand the algorithm, the quantum circuit is divided into different stages. The first stage is referred to as ket psi 1, the second stage as ket psi 2, the third stage as ket psi 3, and the last stage as ket psi 4. Ket psi 1 is equals to ket 0 tensor product with ket 1. To calculate ket psi 2, we apply Hadamard gates to ket psi 1. Thus, ket psi 2 will be equals to 1 over square root of 2 raised to the power n times the summation of all the n qubits combinations. Applying a Hadamard gate to the second register will gives us ket 0 minus ket 1 divided by the square root of 2. Note that this is referred to as ket minus. To calculate ket psi 3, we have to apply UF gate to ket psi 2. Remember that if the input to the UF gate is ket x and ket y, its output will be ket x and ket f of x XORed with ket y. Thus, upon applying UF gate to ket psi 3, the first registers remain unchanged, where the second register is transformed to ket f of x XOR with ket 0 minus ket f of x XOR with ket 1 divided by the square root of 2. F of x XOR with 0 is equals to f of x, whereas f of x XOR with 1 is the complement of f of x. We substitute these values into ket psi 4 to simplify it further. Note that when f of x is equals to 0, the second register will have ket 0 minus ket 1 divided by the square root of 2, which is essentially saying the second register will have ket minus. In contrast, when f of x is equals to 1, the second register will have ket 1 minus ket 0 divided by the square root of 2, which is basically minus of ket minus. This shows that we will have a minus sign if and only if f of x is 1. Therefore, we can rewrite the second register as minus 1 raised to the power f of x times ket minus. Let me clear the blackboard to make some space. Ket psi 4 is calculated by applying the Hadamard gate on the first register only and keeping the second register as it is. In fact, we do not need the second register for our future calculation. So, I will not be writing it from here onwards. Oh, I forget to include minus 1 raised to the power f of x in my ket psi 4. Let me make this correction here. All quantum gates represent linear functions. Therefore, I can take the Hadamard gate inside the summation and apply it on ket x. The application of Hadamard gate on ket x transforms it into an equal superposition of all n qubit values of a variable y. The sign of these values depends on both x and y. Therefore, we can express it as minus 1 raised to the power x and y. If you still have any confusion in understanding the operation of the Hadamard gate, I strongly recommend watching my series of videos where I explain this gate clearly. Anyway, to simplify ket psi 4, we rearrange the two summations. We take our both instances of 1 over square root of 2 and multiply them, resulting in 1 over 2. Furthermore, we multiply minus 1 raised to the power f of x and minus 1 raised to the power x and y, which results in addition of exponents, and we get minus 1 raised to the power f of x plus x and y. That's it. We are now ready to measure our first register. Consider a case where the function is constant. In this scenario, we claim that we can measure y as ket 0 with a probability of 1. Let's verify this claim by calculating the probability of measuring ket 0. Firstly, note that x and y will be 0 as y is ket 0. With a constant function, we will either always get f of x is equals to 0 or f of x is equals to 1. If f of x is equals to 0, then minus 1 raised to the power f of x will always return 1. Thus, in the numerator, we have the summation of all ones resulting in 2 raised to power n. The numerator and the denominator cancel each other, making the amplitude of measuring ket 0 equals to 1. Scaling this amplitude gives us a 100% probability of measuring y is equals to ket 0. In contrast, when f of x is equals to 1, then minus 1 raised to the power f of x will always returns minus 1. Thus, in the numerator, we have the summation of all minus 1s resulting in minus 2 raised to the power n. The numerator and denominator cancel each other, making the amplitude of measuring ket 0 equals to minus 1. Scaling this amplitude of minus 1 will once again gives us 100% probability of measuring y is equals to ket 0. In conclusion, when the function is constant for both f of x is equals to 0 and f of x is equals to 1, we will measure y is equals to ket 0 with 100% probability. So we have verified our claim. Now consider the case when the function f is balanced. The claim is that in this scenario, we will never measure y is equals to ket 0. Let's verify this claim by computing if the probability of measuring ket 0 is 0 or not. Once again, x and y will be 0 as y is ket 0. When f is balanced function, then half, that is 2 raised to power n minus 1, of its input will return minus 1, and the remaining half, 2 raised to power n minus 1, will give an output of plus 1. This means the summation will become equals to 0. The 0 amplitude when scared gives us a 0 probability of measuring y is equals to ket 0. In conclusion, when the function is balanced, we will never be able to measure ket 0. Hence, we have verified our claim once again. Let's consider an example in which n is equals to 2. The function f is balanced in this example. The function returns 1 on input 0, 0 and 1, 1. Otherwise, it returns 0. Ket psi 1 will be equals to tensor product of ket 0, 0 and ket 1. In ket psi 2, we apply Hadamard gate to the both registers. The first register transformed into 1 over 2 times ket 0, 0 plus ket 0, 1 plus ket 1, 0 plus ket 1, 1. The second register will have ket minus. In ket psi 3, we apply UF gate to the registers. Since the second register has ket minus, the UF gate will change the sign of all the inputs which are providing an output of 1. Hence, ket psi 3 will be equals to 1 over 2 times minus ket 0, 0 plus ket 0, 1 plus ket 1, 0 minus ket 1, 1. In ket psi 4, we need to apply a Hadamard gate to the first register. There will be 16 terms, but we can calculate them easily using the clever tabular method discussed previously in a video. Ket psi 4 will result in minus ket 1, 1. Scaling the amplitude of minus will give a 100% probability of measuring y as ket 1, 1. Since y is not equals to ket 0, 0, we can conclude that our function is balanced. That is it for this video. See you later. Goodbye.